Hello friends, continuing with the chapter of atom. Today we come to its third part, that is energy level diagram of hydrogen atom. Energy of an electron in nth orbit of an atom is given by the expression En is equal to minus 13.6 Z square by N square electron volts. I repeat, energy of an electron in nth orbit of an atom is given by the expression En is equal to minus 13.6 into Z square by N square electron volt. For hydrogen atom, Z is equal to 1. Therefore, for hydrogen atom, energy expression would be En is equal to minus 13.6 divided by N square. Okay. Now, for first orbit, N is equal to 1. Therefore, energy of an electron in first orbit of hydrogen atom is, say, E1 equal to minus 13.6 divided by 1 square is equal to minus 13.6 electron volts. For second orbit, N is equal to 2, and energy would be, say, E2 is equal to minus 13.6 divided by 2 square, and it is equal to minus 3.4 electron volts. Now here you look at the diagram. Here N is equal to 1 and energy is minus 13.6 electron volts. This is first energy level. N is equal to 2, energy is minus 3.4 electron volt, and is the second energy level of hydrogen atom. Now for third orbit, N is equal to 3, and energy would be, say, E3 is equal to minus 13.6 divided by 3 square, that is minus 13.6 divided by 9, and it is equal to minus 1.51 electron volt. And here you have, for N equal to 3, energy is minus 1.51 electron volt. So it is third energy level. Now for fourth orbit, N is equal to 4, and energy would be, say, E4 is equal to minus 13.6 divided by 4 square, or it is equal to minus 13.6 divided by 16, and it is equal to minus 0.85 electron volt. And here when you look at the diagram, here we have shown N equal to 4 and energy is minus 0.85 electron volt, and is the fourth energy level. And so on, we can calculate energy levels of hydrogen atom. Therefore, energy level diagram of hydrogen atom can be drawn as shown. Now, conclusions drawn. First conclusion is that this energy level diagram shows that electrons are revolving in closed circular orbits called as stationary orbits. And second, energy exists in discrete packets and is said to be quantized. Because when you look at this energy level diagram, there is no energy existing between N equal to 1 and N equal to 2, N equal to 2 and N equal to 3, and N equal to 3 and N equal to 4. So these are discrete packets of energy, and electrons are stationed in fixed orbits. Because they have fixed energy, so they are stationed in fixed orbits, which we call them as stationary orbits, because electron is stationed in that orbit. So these are the conclusions that we have drawn from this energy level diagram. Now assignment 12 continued. Question number 10. Calculate energy of an electron in ground state of hydrogen atom. Number 2, lithium atom. Question number 11. Radius of fourth orbit of hydrogen atom is 0.85 nanometer. Calculate velocity of electron in that orbit. After learning about energy levels of an atom of any element and hydrogen in particular, we come to understand about hydrogen spectrum. Now, to learn about hydrogen spectrum, we need to derive Rydberg's formula. Now, how we can derive Rydberg's formula? Let us see. We start with energy of an electron is given by the expression En is equal to minus half mc square alpha square z square by n square. Let us mark it as equation 1, where c is velocity of light, alpha is fine structure constant, z is atomic number, n is number of the orbit, and m is mass of electron. Now consider third postulate of Bohr's atomic model, which is mathematically expressed as EI minus EF is equal to H nu IF. Let us mark it as equation 2. Here I stands for initial and F stands for final. So E initial minus E final is equal to H nu initial final. That is when an electron jumps from initial orbit to the final orbit. Now, substituting the values of EI and EF from equation 1 in equation 2, we get EI minus EF is equal to minus half mc square alpha square z square by ni square minus within bracket minus half mc square alpha square z square by nf square, and it is equal to h nu if, or h nu if is equal to half mc square alpha square z square common within bracket 1 by nf square minus 1 by ni square. Now we replace nu equal to c by lambda, that is nu if is equal to c by lambda if. Therefore, we can write here hc divided by lambda if, because nu if is equal to c divided by lambda if, equal to half mc square alpha square z square within bracket 1 by nf square minus 1 by ni square. Or 1 by lambda if is equal to half mc alpha square z square by h into 1 by nf square minus 1 by ni square. Let us mark it as equation 3. Now substituting the value of m, alpha, h and c in equation 3, we get 1 by lambda if is equal to half into 9.1 into 10 raised to power minus 31 kg mass of electron into 3 into 10 raised to power 8 meter per second velocity of light into 7.29 into 10 raised to power minus 3 square fine structure constant divided by 6.62 into 10 raised to power minus 34 Planck's constant into z square into 1 by nf square minus 1 by ni square, or we can write it as 1 by lambda if is equal to r z square within bracket 1 by nf square minus 1 by ni square, where r is equal to 1 by 2 into 9.1 into 10 raised to minus 31 into 3 into 10 raised to power 8 into 7.29 into 10 raised to power minus 3 square divided by 6.62 into 10 raised to power minus 34. And on simplification it comes out to be 1.09858 into 10 raised to power 7 per meter and is known as Rydberg's constant. The wavelength of light emitted when electron jumps from initial to final orbit is, say, lambda IF is equal to 1 by RZ square into 1 by NF square minus 1 by NI square. I repeat, wavelength of light emitted when electron jumps from initial to final orbit is, say, lambda IF is equal to 1 by R by Z square into 1 by NF square minus 1 by NI square, bracket closed. Now we have taken here the reciprocal of this equation, okay, and is known as Rydberg's formula. Now, theory of hydrogen spectrum. Consider Rydberg's formula. Lambda IF is equal to 1 by RZ square into 1 by NF square minus 1 by NI square, bracket closed. For hydrogen, Z is equal to 1. Therefore, formula reduces to the form lambda IF is equal to 1 by R bracket start 1 by NF square minus 1 by NI square, bracket closed. Now, since 1 by R is equal to 912 angstrom, therefore, wavelength of light emitted is given by the expression lambda IF is equal to 912 divided by 1 by NF square minus 1 by NI square angstroms. Okay. So this is the formula by which we will calculate the wavelength of light emitted when electron jumps from higher orbit to lower orbit. Now, case 1, consider the expression lambda IF is equal to 912 divided by 1 by NF square minus 1 by NI square angstrom. When NF is equal to 1 and NI is equal to 2, 3, 4, 5, so on, ultraviolet radiations are emitted. The range emitted is 912 angstrom to 1216 angstrom and is known as Lyman's series or UV radiation. So here you can see this is Lyman series or UV radiations. When electron jumps from second to first, third to first, fourth to first, and so on. So here you can see here this is Lyman series. Okay. Now case 2, consider the expression lambda IF is equal to 912 divided by 1 by NF square minus 1 by NI square again. Now when NF is 2 and NI is equal to 3, 4, 5, 6 and so on, visible radiations is emitted. The range emitted is 6566.4 angstrom to 3648 angstrom and is known as Balmer series. Here you can see this is Balmer series where electron jumps from third to second, fourth to second, fifth to second, sixth to second and so on. Now here you You have Balmer series. You can look into the diagram clearly. These are visible. Jumps are visible, and you can think of Balmer series. It is visible spectrum, and you can calculate, of course, the values, that is the range which is emitted, by putting n first nf equal to 2 and then ni equal to 3, 4, 5, 6, so on. For the last one you can put infinity, ni is infinity for the last one. Okay. Case 3. Consider the expression lambda if is equal to 912 divided by 1 by nf square minus 1 by ni square angstrom again. Now when nf is equal to 3 and ni is equal to 4, 5, 6, infrareds are emitted. The range emitted is 18,761 to 80,208 angstrom and is known as Paschen series. So here this is Paschen series. Okay. Now first spectral line is jump from 4 to 3 and last spectral line would be jump from infinity to 3. So that way you can have the spectrum of infrared radiations emitted for this case. So here you have Paschen series. Now fourth case. When nf is equal to 4 and ni is equal to 5, 6, 7 and so on, near infrareds are emitted. The range is 40,533.3 angstrom to 14,592 angstrom and is known as bracket series. So here this gives you bracket series, and here is the bracket series. When electron jumps from 5th to 4th orbit, 6th to 4th orbit, 7th to 4th orbit and infinity to 4th orbit, this constitutes bracket series, and it ranges from 14,592 angstrom to 40,533 angstroms. Now fifth case, consider the expression lambda if is equal to 912 divided by 1 by nf square minus 1 by ni square angstroms again. Now when nf is equal to 5 and ni is equal to 6, 7, 8, 9, so on up to infinity, far infrareds are emitted. The range is 74,618.18 angstrom to 22,800 angstrom and is known as Fund series. Now here you can see this is a Fund series. Also here this is Fund series. That is when electron jumps from 6th to 5th orbit, 7th to 5th orbit, 8th to 5th orbit and so on up to infinity to 5th orbit. Fund series is emitted and spectral lines range from wavelengths 22,800 angstrom to 74,618.18 angstrom and are known as far infrareds. So you actually substitute the values of nf and ni as given here or mentioned here and calculate the range. You should verify the range I have given to you. So you will come to know about the wavelengths of different ranges, lower limit and upper limit. Okay. Now Lyman series is ultraviolet, Balmer series is visible spectrum, Paschen series are infrareds and bracket series is near infrareds and fund series is far infrareds. So this is how we can explain theory of hydrogen spectrum. Now assignment 12 continues. Question number 12. Calculate first and last spectral line in case of hydrogen atom in the following cases. Number 1, ultraviolet radiations. Number 2, Balmer series. Number 3, Paschen series. Number 4, bracket series. And number 5, fund series. Now question number 13. The spectrum of a star in the visible and ultraviolet regions was observed, and the wavelength of the lines that could be identified were found to be 824 angstrom, 970 angstrom, 1120 angstrom, 2504 angstrom, 5173 angstrom, and 6100 angstrom. Which of these lines cannot belong to hydrogen atom? And you identify which are the wavelengths which do not belong to hydrogen atom. Given Rydberg's constant 1.03 into 10 raised to 7 per meter and is equal to 970 angstrom. Support your answer by suitable calculation. Now quantization condition from wave mechanic picture. According to wave mechanic picture, lambda de Broglie, that is lambda d is equal to h by p. Let us mark it as equation 1. Now when an electron is confined to circular orbits, then circumference of nth orbit contains exactly n de Broglie wavelengths, that is 2 pi rn is equal to n lambda d, where 2 pi rn is the circumference of nth orbit and lambda d is de Broglie wavelength. Okay. Or from here we have lambda d is equal to 2 pi rn by n. Let us mark it as equation 2. Now comparing equations 1 and 2, left hand sides is same, that is lambda d and lambda d. Therefore the right hands must be same, therefore h by p must be equal to 2 pi rn by n. Now from here we have prn is equal to nh by 2 pi. Or replacing p by mv, we have mvrn is equal to nh by 2 pi, which is second postulates of Bohr's atomic model and is the quantization condition. So thus we can derive quantization condition from wave mechanic picture. Assignment 12 continued. Question number 14. State Bohr's postulate for the permitted orbits for the electron in hydrogen atom. Use this postulate to prove that the circumference of the nth permitted orbit for the electron contains exactly n wavelengths of the de Broglie wavelengths associated with the electron in that orbit. Okay, you answer the questions on the basis of the text that you have learnt. Thank you so much. Next time we'll take up the fourth part of it, that is size of nucleus. Once we have studied that the atom has extranuclear part which contains electrons and the nucleus which contains protons only, and we are to now study about the nucleus. So far we were dealing with the extranuclear part in Bohr's atomic model. Now we will deal with the central nucleus, where we will study about the size of nucleus. Okay. Till then, goodbye and good luck to you.